Hi, this is a recording to replace the lecture that we should have had last Thursday over the last bit of chapter 16. Thank you for your patience. I went to start cutting and pasting the figures into this whiteboard application that I have that we look at in class, and lo and behold, they updated it and disabled cut and paste. So I have managed to find a workaround, so let's see how this goes. It's a little bit clunkier than before, but we'll give it a shot. So I would have started off with problem 1664. It is a rotation problem having to do with velocities. And we are, by the way, not covering all of chapter 16. I'll talk more about that later. So 1664 says the pinion gear A rolls on a fixed gear rack B with an angular velocity of omega equals 4 radians per second. Determine the velocity of the gear rack C. So right now I'm going to cover two different ways to do this. Then we're going to come back and do a third here in a little bit of time. You can in general pick the way that you want to do it on the test. I will probably have two problems that ask you about the instantaneous center of zero velocity, which we've not covered yet. That will be one of the methods I will show this for. The rest of the time you can pick whatever method you want. Okay, now it says pinion gear A rolls on the fixed gear rack B. Okay, so B is fixed. Okay, so since B is fixed, we know that the velocity of B is equal to 0, right? Okay, now one way is to do it with rather kind of like a scalar approach. Okay, the other is with a vector approach. I'm not going to ask you to do it with, vectors versus scalars. You do whichever one you want. Like I said, I will probably ask you to do two, one of each type, which we'll talk later about the instantaneous centers. But if you use a vector or a scalar approach, it's totally up to you. So remember what we've been doing is v sub c is equal to whatever the velocity b is plus v sub c with respect to b. Okay, now that's the approach for both of these. Okay, but we're going to try to do it in a scalar approach first. So we have to pick a direction for being positive. So let's say left is positive, just kind of being different. Okay, so we would say I don't know what v sub c is, but if this is rolling this direction and b is fixed, as this gear rolls counterclockwise, it's going to push this way. Okay, everybody agreed? So v sub c is going to go to the left. V sub b, since it's fixed, is 0. And remember that v, by definition, is omega r. Okay. Okay, so I need to talk about c with respect to b. So it does say omega is 4 radians per second, and that's the angular velocity for the entire gear or disc or whatever it is that you have. So this would be 4 radians per second, and the radius would be 0.6. Well, it's not a radius. It's 0.3 is the radius, but r is the distance. Okay, so this would be twice that, which is 0.6. Okay, so v sub c is 2.4. And since it's a velocity, it's feet per second. And since it's rolling this direction, then it is going to travel this way. So it's going to go to the left. So I feel pretty good about that. So this is this approach. Now the other approach is the vector approach, and we would do it with I, j's, and k's. And so it has a lot of thought to go into it. So v sub c, we go, I don't know what its magnitude is. It has some magnitude, v sub c. It would move left or right, and we're saying it's going to move left, so let's say that's negative. V sub b is 0, so it doesn't have an I, J, or K. Now, here we go. So v sub c with respect to b in this case, okay, v sub c with respect to b in the case of a vector is omega crossed with r of c with respect to b. Remember, you have to be careful that omega comes first. Okay, so omega is a magnitude of 4. Now, remember when we try to decide whether it's I, J, or K, it's spinning counterclockwise like this. So if you take your fingers, your right hand, and you take your fingers and you curl your fingers in the counterclockwise direction, your thumb is going to point toward you, and that's the positive K direction. So this would be a positive K, and it's going to cross with R. Okay, so R is going to go from here to here. Since I'm going all, it's not really a radius, even though I said radius over here. It's the distance. So we're going to go, it's 0.6, and since I'm heading straight up, we've got I, J, and K is coming out of the board like your thumb. This would be J. Okay, now to do a cross product, we also have to have that little circle that goes I, J, K, going counterclockwise positive. Clockwise is negative, kind of like trig class. Okay, so here we go. So I've got minus v sub c I is equal to, well, 0, 0. Okay, 4 times 0.6 is 2.4. Now, K cross with J, we go K cross with J yields I, so this would be an I. And since I'm going this direction, this would be negative. So this is a negative 2.4i. And then setting these two things equal, negative v sub c is equal to negative 2.4. So v sub c is equal to 2.4 feet per second. Now it's the same answer we had before. You may prefer scalar over vector approach. I think that with the scalar approach, you really have to have a gut feeling for what's happening more than with the vector. The vector sort of takes care of itself. So let's move on. Hopefully this new program will let me move on. Let's do another problem. And this is kind of the same, but a little ramped up. And it says the pinion gear rolls on the gear racks if B is moving to the right at 8 feet per second. So this one is going 8 feet per second. Okay. And C is moving to the left at 4 feet per second. Determine the angular velocity of the pinion gear and the velocity of its center at A. All right. So in this case, they tell you the velocities of the gear racks, and then you're supposed to come up with omega and velocity of the center. All right. So we've got one velocity going left, one velocity going right. So let's do the scalar. And then we'll do the vector. Right. So in this case, let's try going to the right's positive. Keep our interest. Right. So I'm going to do v sub c is equal to v sub b plus v sub c with respect to b. Okay. So v sub c would be minus 4 because it's going to the left is equal to 8, which is going to the right. Now, I don't know what, remember v is equal to omega r. So I don't know what omega's value is, so we're just going to say it's omega, and r would be the distance, so that's 0.6. But since it's spinning this way, it would yield a velocity that's going to the left, so this is minus. So when we solve this out, we get omega c is equal to 20 radians per second. Keep track of your units. So then we have v sub a would be equal to v sub b plus v sub a with respect to b. So v sub a would be 8 minus 20. That's the same omega that you had before. So this one is this one times 0.3 because that's r. We're only, in this case, we're only going from B to A, so that's 0.3 is your distance. So V sub A ends up being 2 feet per second. Okay, now if you do it as a vector, you've got V sub C is equal to V sub B plus, and let's go ahead and write in the omega and the cross product. All right, so we would have minus 4I equals 8I plus, I don't know what, remember we're going to do the same problem, so I don't know what omega is technically at this moment. Omega, and if you curl your fingers in the direction that this omega is going to spin at, then your thumb points out at you, so that's a positive K. And then we cross it with the distance, which is 0.6J. And remember, we have that I, J, K, which I'm not going to give to you, so you need to know how to do this. Right, so this is plus, because unless it's on the inside cover of your book, and I haven't frankly looked, but I don't remember it being there, so you'll have to remember that. So then you would get minus 4I is equal to 8I minus 0.6 omega Ci. This equals, so stripping out your I components, you get minus 4 is equal to 8 minus 0.6 omega. So omega is equal to 20 radians per second, which is really, you know, same value you had before. Right there. Right. So then you would go V sub A is equal to V sub B plus omega A cross with R A with respect to B. So V sub A, I don't know its magnitude, is equal to 8I plus, okay, 20 is your omega from before. Since it's going counterclockwise, your thumb would point out at you, so it's positive K crossed with 0.3J. So V sub AI is equal to 8I minus 6I. So V sub A would be equal to 2. Now I'm going to come back and do this problem again later using another method, and frankly I'm kind of worried about when we get there, because I understand that this new system will not allow me to really erase bits and pieces. So we will be experimenting. All right. Now, the next section, which is 16.6, is going to talk about a technique that you can use. It doesn't work on every problem because there isn't an instantaneous center of zero velocity. And so, but when it does tend to make your world simpler and yet more complex at the same time. So you'll just have to deal. Okay, so it's just one of those things where you're like, how do things make things simpler and more complex at the same time? Well, you'll know here in just a minute. And I'm going to try to erase this I, J, and K circle just for the fun of it. Oh, look at there. Maybe it's going to let me erase bits and pieces when I come back, just so that we can see. Now, here's somebody on a bicycle. This is a picture in your book. And so if you look at the bicycle, they do talk to you about how right down here, if you, I'm not sure I'm going to be able to get a different color at this point in time. All right, so we would be doing black for this whole thing. So, but right down here at the bottom of the wheel where it's touching the ground, you can kind of imagine that the wheel is contacting the ground's not moving. So just for that instant, that point of the bottom of the wheel is static. It's just staying right there, and the rest of the wheel is spinning around it. You can see how it blurs more up here, and it becomes a little bit more clearer here, and then it becomes the clearest here. So if you can kind of imagine, it's almost like the wheel is trying to spin around that pivot point. Okay. Now I can see what they're saying about erasing parts makes all of it go away. So this point right here, when you have a disc, a wheel, or something without slipping, you know, if you take off on your car, the wheels will spin. I guess technically you possibly do that on your bike. If you were on gravel, I've seen it done on gravel, but I haven't seen it really done on a solid surface. I'm guessing you could try. Anyway, so they're talking about there's sometimes a little tiny point on the body of the object where it is stationary and everything else is trying to spin around it. So there's 3 cases. What they're gearing at is, we have this general formula we're working with. Okay, and what they're saying is, if by some magic process or some miracle or whatever, we could get v sub a to be 0, then this just reduces to v is equal to omega r, right? Now it might be vectors, but it still reduces to something that is very simple. So if we could just magically find out some way that this v sub a was equal to 0, and if you'll remember, what we're going to come back here later in a little bit is right over here on this first problem. When we were doing this first problem, this point B, right, is attached. Well, the gear is attached at point B, and point B is not moving, right? So it's kind of like the bicycle wheel on the ground. So right here, you can tell that this is an instantaneous center of 0 velocity. So here's my 0 over here. Okay, so they're saying, if we could just find a reference point where this value is 0, that just reduces it to a very trivial multiplication and we can just be done. So that's what we're aiming at. So when we come back, we'll do it that way. Now there's some specific cases they're going to do in this book, and so there's 3 cases. I call them case A, B, and C, right? So case A is, and they give you these pictures, okay? So case A says that if you have the velocity of a point that's known as and here would be your known velocity. Excuse me. And you have some angular velocity. Okay. Then there's some point back here that's an instantaneous center that this is technically spinning up around. Okay. And you can find that from the fact that it's just spinning around that one point, from the fact that r is equal to v over omega, right? So this would be v sub a. And so this r is this distance, but since we're talking about instantaneous center, and that IC stands for instantaneous center of 0 velocity. So this would be r of a. Okay, IC. That's how they usually show it. If it's not debatable, sometimes they just say R of IC, but in most of our cases, it's going to be debatable which distance you're using, so let's try to get into a good habit. This case here, I call case B, and it says, what if we have the lines of action of 2 non-parallel velocities? Okay, so here's a velocity. Here's another velocity on some object that's spinning like this. Because you can imagine, if this velocity is pulling down and this is pulling down and to the right, it would cause this to spin. Okay, so if I have 2 velocities given, and they're not parallel to each other, because there's another case for that. So if they're not parallel to each other, then what I do is I find this direction for V. Okay, and then I draw a perpendicular to it. Now, hopefully this just resumed. All right, if you could draw a perpendicular this direction, or you could draw a perpendicular this direction. But what I'm trying to find in this particular case is an intersection point. So if you draw out this way, and you draw perpendicular to V sub B, do you see how these 2 ends never intersect? Okay. So I'm going to draw in toward each other. And where these two perpendiculars to the velocity intersect, this is the instantaneous center of zero velocity. See how they say velocity is equal to zero right there? And in effect, for just that instant, this object is spinning around this point. Now, that is, when they call it the instantaneous center, they literally mean that. It's only good typically for an instant while these angles are this direction. Once it moves on and it rotates and it's somewhere down here, okay, and you would have some different velocities going on, the instantaneous center is somewhere else, right? So this is only true for this one instant in time, okay? Then here's two cases, okay? This is where the velocities are parallel to each other. A lot of times this happens with things like those discs that are rolling on the ground or on those gears. So here's v sub a going this way. Here's v sub b parallel, but it's going the opposite direction. So what you would do is, oh, well, let me back up here just a second. All right, so I just blitzed through here thinking that you would probably understand, but I want to bring this up. So the way you find this instantaneous center is with trig. So you're going to have to go back and brush up your trig if you don't know. So here we go. So I start the tails right here. I line them up over each other. Okay. Then I connect the two. And then I kind of connect the dot between the two heads of the vectors. So you need to, they don't have to be exactly the scale, but it would be helpful if they would be closely in the order of magnitude of to scale, you know, so that if b sub a is a smaller amount, it's shorter than b sub b. So try to get them in the general framework of, is b sub a smaller than b sub b or larger than b sub b? And where these two lines intersect, that's your instantaneous center. And so it is, sometimes you have to use trig and sometimes you can just use similar triangles. This one says, what if you have v sub b and v sub a on some object like a disk, you know, and so it could be going like this. Then if they're parallel, you extend, you still put the two tails above each other. You extend this off and you're going to use similar triangles to get where the instantaneous center is. One of the things I said in the update is that you can choose to make your little lines have an arrow on the end of it. I am not choosing that, and it's just putting, I didn't choose that, and it's just putting arrows on everybody. So I hope that that doesn't confuse you, because I just noticed that I've got little arrows all along there. I was trying to do dotted lines. Okay, I am not a fan of this new update. I've already let them know that. So we will move on. Now, in the at the end of this section, they have this preliminary problem section, which normally I don't talk to you about, but I thought these were pretty good. And so on page 367, that's fun. Now my E's have arrows on them. Okay, so on page 360, goodness. Okay, how do I make this turn off? Let's see if I can make it not do that. Okay. Okay, oh good, let's try page 367. Sorry that I'm having fun at y'all's, you know, during y'all's lecture time, but it's either laugh or cry at this point. All right, so this is the preliminary problems, and they just ask you to try to identify where you would be looking for the instantaneous center. So it says establish the location of the instantaneous center of zero velocity for finding the velocity of point B. So if you have a disc or a bicycle or a car wheel or something else, you know, a gear, and it is contacting a surface and there's no slipping, you know, so you're not spinning, you know, spinning your tire and not getting anywhere, this would be the instantaneous center of zero velocity right here. Just like with the bicycle picture. Okay, now here's one where you've got a velocity that's going this way, that's 4 meters per second, and a velocity that's going this way at 3 meters per second, so it's a little bit less than the 4. You would set these up, you would draw a vertical, you would then connect these end pieces right here. This would be a triangle of length 4. This would be a triangle of length 3. You know, you would say that from here to here was 2. Then you could say, I think your book uses X, you know, I could use D. If this distance right here was D, then this distance right here is 2 minus whatever D is, right? Right? If this distance right here is D, from the top to the instantaneous center is some distance D, then the remainder of the distance, since this is 2, right, this is 2 meters, is 2 minus whatever D is. And you would use similar triangles to figure that out. This one, okay, is one of those cases where you have the non-parallel velocities. So you know if this omega is going this way, then the velocity runs perpendicular to the axis that the omega is related to, right? If omega goes this way or the other way, it doesn't really matter. This link right here is the axis, and at the end of it, perpendicular to it, would be vis a vis. Okay? And then they tell you, now, if this is spinning down like this, so this is going to drag down like this drags down, it pushes down on A, and as A pushes down, B is going to slide this way, right? Okay? So if B slides this way, this would be some value for vis a B. Now we're going to draw perpendicular to the velocities, right? So technically I could draw perpendicular this way, perpendicular that way, but do you see how if I draw perpendicular, now let's not do it up there. I don't know why I did that. Here's its point of application. I don't know that you can see it. Okay, let me see if I can make this bigger. So if I draw perpendicular to this point, point A, not anywhere along point A, but just at this physical point right here. Do you see that going this direction and this looking that direction, there's no intersection point? Agreed? So I don't have to draw that side. I really only need to draw back. So I'm trying to find an intersection point. So look over the velocities, and if you can't tell, draw both directions. Okay, I get that. You're tired, got a lot going on in life. If you can't tell, draw both directions and go, okay, there's no intersection out here, right? So this right here would be my point of intersection, and then I would use trig to figure out where that was actually located. Okay, now let's go here. If this one is spinning this way, then this is going to be my velocity. It's going to run it this direction, as a matter of fact. So as this goes this way, and it's going to push it down, right? Then this is going to kind of arch over toward this direction. And then it's going to drag this, but this can only go, say, this direction. Okay? Now if I draw perpendicular, this would be the perpendicular, and this would be the perpendicular. But do you see that whether I'm looking up here or down here, or looking down here or up there, there's no point here where they're going to intersect? Do you see how they're not going to angle back and find some sort of point of intersection back there? So there is no intersection. So there is no instantaneous center of zero velocity. Okay, everybody all right? Now, just to kind of give you a heads up, let's look back over here. All right, do you see how this figure right here has two links, right? It has one link right here, one link right there, and then it's got a block that's pushing along. Okay, and do you see how this one has 3? 1, 2, 3. Okay, for the purposes of what you're responsible for in this section, it's just the ones with 2. Okay, so I think in the exercises there's only one like this. Maybe No, I take that back. I think there's some weird, kind of more weird looking ones, toward the end. But we are going to stick, for the purposes of our test, you have to know the ones with 2 links. Okay, so like 2 links in a block or something like that. So you have to know those. You do not have to know the ones with 3 links, or the really, really weirdly complicated ones. Now, let's go back to 16, 64, and 65. So we're going to scroll all the way back over here. If I ever get back there. All right. Now, so this is the one. All right, which is basically that kind of case A, where you've got your instantaneous center here at the base, and this would be your V sub C. And so looking for V sub C, you would go, oh, V sub C is equal to omega R. Okay, C. And sometimes what they do is they'll say it's like I sub C to C, and I think that's a good notation. So we're going from the instantaneous center to C, because this is a distance, right? So then you could say, well, omega is 4, and R from the instantaneous center to C is 0.6, because it's not the radius, and this turns out to be 2.4 feet per second. So this instantaneous center reduces this down to just this part right here. Okay? All right. Now, this one, where we had 4 going this way and 8 going this way, this is like one of those last 2 cases where you had parallel vectors and you had to try to find an intersection point. So what would happen is you would say, all right, I've got 4 feet per second this direction, and then I'm going to line it up down here, and 8 goes this way. And 8 needs to be, kind of bigger than it helps you to have a gut feeling of confidence in your answer if you try to get it to scale. So this is 8. Okay. Then you draw a vertical, and then you draw from head to head. Okay, so you draw this vertical between that tails. They connect the dots here. Okay, now according to what they wrote, this was 0.6 feet. Okay, and I'm trying to figure out what this instantaneous center, where its location is. Everybody with me so far? All right, so then I can use similar triangles. And let's say that this right here is some value d. So this distance right here is d. Then this distance would be 0.6 minus whatever d is. Agreed? Or you could do it the other way around. You could put d on the bottom, 0.6 minus d on the top. Then you can say d is to 4 as 0.6 minus d is to 8. So 2d is equal to 0.6 minus d. So 3d is equal to 0.6. d is equal to 0.2. Now, that's 0.2 from the top. Okay, remember? Because d's right here, it's measured from the top. And so it would be 0.4 from the bottom. And if you look up here, see how this right here is saying it's closer to the top than it is the bottom? And if you try to draw it a little bit to scale, do you see how this is a little bit closer to the top than the bottom? So it gives you a better feel for Okay, I think I'm in the right ballpark. So then what you can say is V is equal to omega RIC to C. So 4, okay, that's using the number at the top, is omega. And what's the distance between the instantaneous center and C? Okay, this would be, C is the top, right? Let's go back up here. C is the top, B is the bottom. All right, so if I use C, then this would be 0.2 from the top. Okay, so omega turns out to be 20 radians per second. Okay. Now, or, because we're trying to find omega for the whole disk, so it would be the same whether it's C or B, we could use point B. Okay, so 8, using the velocity that's on the bottom, okay, is equal to omega, and the distance from the instantaneous center to B is this 0.4. So omega turns out to be 20 radians per second, which is what we had before. Okay. Then it asks us about V sub A, and V sub A, right, let's talk about it. Now, where is A? It's at the center, right? Which is 0.3 from the top and the bottom. Okay, now if it's 0.3 from the top and the bottom, so look, let's look right here. If it's 0.3 from the top to the bottom, it is 0.1 below here, right? Everybody okay so far? So you could say V sub A is 0.1 times 20 radians per second. So it's 2p per second. Because here's A, and here's your instantaneous center. Okay? All right. Enough of that one. So let's go over here. Go back kind of where we were. Way back over here. All right, so this one says the conveyor belt is moving to the right at 12 feet per second. At the same time, the cylinder is rolling counterclockwise at 6 radians per second. While its center has a velocity of 4 feet per second to the left. Oh, no, wait a minute. That's not the one that I wanted to do. Well, this is one of the wonderful worlds of this new system. Okay, so we're going to use the same figure, all right, but we're going to change up this. Okay, same figure, and we're going to do 1684. All right, and it says the conveyor belt is moving to the right at V is equal to 8 feet per second. So, all right. At the same time, the cylinder is rolling counterclockwise at omega is equal to 2 radians per second without slipping. Determine the velocities of the cylinders center C and point B at this instant. Okay. Alrighty, so we've got this conveyor belt that's moving to the right. The cylinder is rotating counterclockwise, so it's going like this. But as it rolls, and it's not slipping. Okay, so if it's not slipping right here, it's all going to travel like this. Okay, so what we've got is that case where things are parallel. So we've got the conveyor belt's going 8 feet per second. Okay, V sub C, V sub B, and then somewhere back here I've got an instantaneous center. So this distance from here to V sub C right here is 1. Then up to V sub B is 1. Okay, so this is 1, this is 1. I don't know what that distance is right there. All right, but if I use similar triangles, and work this through, then I can find that what happens, because this is, okay, this red part is the knowns, or my sketching of what's known and what's required. So this part up here is what I'm trying to determine. This is me figuring this out. Okay? So what I can say is that RA to the instantaneous center, okay, let's just call it R of A, is equal to V over omega, right? So R is equal to 8 over 2, because that's your radians per second. And this is your feet per second. So R turns out to be 4 feet. Okay, so this total is 4 feet. So this distance right here is 2. Okay, so here we go. So if, let me draw this. So if this is 2, and this is 1, and this is 1, and this is 8, and this is V sub C, and this is V sub B, okay, then I can say by similar triangles that V sub C is to 3, as 8 is to 4, and so V sub C has to be 6 inches per second. Is it inches or feet? Feet. Feet per second. And also I can say v sub b is to 2 as 8 is to 4. So v sub b is equal to 4. Now the one that's far more complex is this one. All right. So this says at one point I had the instructions or the question over here. I don't know where they are now. So we are going to write them out. All right, so this is 1682, right? And it says determine the angular velocity, which is omega, of link AB at the instant shown if block C is moving upward at 12 inches per second. Okay, so we know that block C is moving this way. It's constrained. Now, here we go. Now, we don't know what omega AB is. That's what I'm looking for. But supposedly it's going counterclockwise. And if it's going in this direction, I follow down this link. And perpendicular to this link is v sub b. And it would be actually working this direction, because if omega is swinging this way, then the velocity is going this direction. But the key here is it's perpendicular to here. Okay. Now, what I'm trying to do is to figure out where the instantaneous center of zero velocity would be. Okay. So I've got a couple of choices. I'm going to draw perpendicular to here, if you go in both directions, and perpendicular to here, if you're going both directions. Well, it's not doing so much over here. All right. So can you see that out here on these ends, they're not intersecting. Okay, so we don't want those ends. We want these pieces right here. Okay. So I need, some of y'all, by the way, are forgetting to put your drawings in on your homework, and I'm taking off points for that because you still have to do drawings because you're not doing 3D. So here we go. So here's what we've got. So I know, I guess, several things. I guess if this is perpendicular to here and this is 30 degrees, so this one's parallel to this one, then alternate interior angles have to be the same. So this one also has to be 30 degrees. Everybody with me? So this one right here has to be 30 degrees. Okay? Now, this right here, right down here at B, is a right triangle. This is a vertical. This is a horizontal. So what I have to do is to say, okay, if this is 30, this right here has to be 60. Agreed? Doesn't this have to be 60 right in here? All right? And if that turns out to be 60, how much is in this entire interior angle right here? So this is 105 degrees. Everybody okay so far? So if this is 30, over here at C is 30, down here at B is 105, then 180 minus 105 minus 30 gets you 45 degrees. And that goes all the way over to here. Okay, so what you've got is this lovely triangle that looks like this. So here's V sub C. V sub B is, I'm kind of drawing it a little bit off, but this is V sub B, right? This is your instantaneous center. Okay, this is 45 degrees. This is 30 degrees. This is 105 degrees. This is your R from your instantaneous center of zero velocity over to C, right? Because this would be C. C? Too many C's. Okay, this would be R. This is your instantaneous center over to B, because this would be B down here. All right. Everybody okay so far? And we know that this is 4 inches. Okay. Well, look, I know all my angles and I know one side. So if I know all my angles and I know one side, can't I use the law of sines? So you can say 4 is to sine 45 degrees. And it doesn't matter which one you do first. R of I, C to B is to sine of 30. Okay, so after you solve all this out, R of I, C to B is 2.8284. Okay, then I can do it again and go 4 sine, it doesn't look like a 4 up there, 45 degrees equals R, I, C to C of sine of 105 degrees. I don't think this whiteboard is as easy to write on because I don't know. Okay, doesn't matter, it's what we've got. All right, so R of IC to C turns out to be 5.4641 inches. All right. Now, all right. The one, we have to start where we have a known, okay? And what we have is a known right here. We know what V sub C is doing, correct? So basically what we're going to do is we're going to kind of alternate our way across. So if you can sort of imagine it, we have a velocity, we know a velocity, okay? Then we're going to find an omega, and then we're going to find a velocity, and then we're going to find an omega until we get to the other end. Okay, so we're just going to alternate our way across, V omega, until we get to wherever it is we want to be. Okay, so we're going to start off with V sub C because we know V sub C. All right, so we would say V sub C is equal to omega BC. Okay, that's this section right here. We're looking at that section. Omega BC. Okay, and we would do R of IC to C. All right. So then we can do, because this part is the part that's controlling this, right? So here we go. So V sub C, which is 12, is going to be equal to omega BC. And we have 5.4641. So omega BC turns out to be 2.1962 radians per second. So I don't know if that kind of creeps you out or anything, but okay, so we had V sub C. We're trying to find this omega. This is the omega we're going to try to find, but we can do it using this instantaneous center. That's the beauty of it, okay? And then we find omega BC. Okay, now that I know omega BC, then do you see how omega BC is actually, the other end of it is point B, right? Here's BC. We were at C, so we were here. Then we came here. Now we're going to here. So we're going to go over to V sub B. Okay, so V sub B is equal to omega BC, okay, R of IC to B. See how we're working our way back this direction, okay? So V sub B, don't know what that is equal to omega, which is 2.1962 radians per second, because we just found that. Times that RIC to B, so it's 2.8284 inches. Okay, so V sub B turns out to be 6.2117 inches per second. Okay, so now we've got V sub B. Now we're going to find an omega. Okay, so we can go V sub B is equal to omega AB times R of AB. Now let's talk about R of AB, right? So we've gone V sub B, which is right here, and they wanted me to find this value right here. But do you see how now I can kind of switch it and say, I've got V sub B, I'm looking for this omega, and I know the length of A sub B, and it's spinning around A, so I can just go over and quit using the instantaneous centers, because for this instant, it's as if the rest of this doesn't exist. And I'm just taking this one V sub B and causing this to rotate around A. So I've got myself over to that point, and I can say V sub B is 6.2117. This is supposed to be inches. Okay. Omega, I don't know. That's my question of the day. And R is 5. So omega AB is equal to 1.2423 radians per second, which is 1.24 radians per second, rounded off. All right. Now, for your homework, I'm going to post that, and we're just going to do just the problems that we, kind of the types that we did here. I'm going to post your homework. I'm just going to have you do a disc, and I'm going to have you do one with 2 links. So I will, with instantaneous centers, okay? So I will post that for you. That will be due, I guess, Thursday. Okay, so homework will be due Thursday. Actually, I may just have you do it and supply you the answers. I'll think about that. So let me think about that, and then I'll post it online and tell you which ones I would have assigned and whether I'm going to actually have you turn it in or not. And then on Tuesday, we're going to start on chapter 17. We're not going to do anything in the rest of chapter 16. So we'll start on 17 on Tuesday, and hopefully this will save nicely, and I will post this evening. Okay, thank you.